Um, we're doing flux integrals, and we just covered what I call the PQR method. Here's the flux integral. Here's the definition of it. Here was the general formula for evaluating this flux integral. And in the particular case where the surface is z is a function of x and y, you can derive this, what I call the PQR formula. So there's a lot of steps to this formula that we can do ahead of time. And we got this guy. I should have mentioned when I covered this that if you had the other types, say x is a function of z and y and z, or y is a function of x and z, you could derive similar formulas to this one. So that would give you three different formulas for those three different types of particular surfaces. In my classes, just so it didn't get out of hand, I limited them to this one. But anyway, let me do some more examples. I did this example last time. Let me do another couple examples and then wrap up all the surface integrals. This one says, evaluate the flux of this vector field through the surface described this way. You got a z is a function of x and y, but it's inside a cylinder. We have to do some three-dimensional thinking in this. In this case, the surface is this inverted paraboloid. And let's see, when z equals 0, you're going to get the radius of that paraboloid is the square root of 5, okay? Take this paraboloid all the way down to the xy plane, the radius would be the square root of 5. It has to be inside this cylinder, which has a radius of 2, which is less than the square root of 5. So the actual surface doesn't come all the way down to the xy plane. It only comes down to wherever this is. And it comes out to a radius of 2. It's going to be the important part, which means what is the shadow of this, or what's going to be the region of integration? It's going to be this surface's shadow on the xy plane, which will be a circle of radius 2. But anyway, let's go through. Here's our surface. Well, here's our f. So P is x, Q is y, R is z. And we have to express everything in terms of x and y only. So we have to make the z part equal 5, this thing, 5 minus x squared minus y squared. So that's what R is. P is x, Q is y, R is 5 minus x squared minus y squared. What's partial of z with respect to x? It's going to be minus 2x. Partial with respect to y is minus 2y. Here's all the pieces. Put them into our formula. Now it's just kind of plug and chug, right? My students love plug and chug. And you finally get this as the integrand. Here's the integral. The region of integration is the unit circle, though. So we're going to want to use polar coordinates again in this example. So x squared plus y squared is going to be an r squared plus 5, and then dA is r d theta. Region of integration is a circle of radius 2. So r goes from 0 to 2, theta goes all the way around. We can break it up as a product. And these last two lines, then, it's just normal double integration. I won't go through that. It's actually pretty easy. Sometimes the moral of the story is we have to kind of think about the surface and then especially what is the region of integration. Here's another one. There's our vector field. P is x, Q is z, R is y. And this is that portion of the cylinder, this cylinder. Y squared plus Z squared equals 4 in the first octant bounded by these numbers. Okay, we got to do some three-dimensional thinking again. This cylinder is along the x-axis, and it has a radius of 2. Through where it went through in the YZ plane, it's a circle of radius 2. It hits Z at 2, it hits Y at 2. It goes along the x-axis. Bounded by, it's in the first octant, so it's going to be where everything is positive. It says X goes out to 3. So here is the surface, sort of quarter barrel up here. What is the region of integration? And that's the important part. All this three-dimensional thinking, the big deal was the region of integration. Thinking about it? This rectangle down in the XY plane. It's the shadow of this surface onto the XY plane. So here's the surface. We can make that Z as a function of X and Y, and it's like this. And it's the positive square root because we're in the first octant. Don't have to mess with plus minus square root here. So here's our surface as a function of Z is a function of X and Y. So the partial of Z with respect to X is 0. With respect to Y is this thing here, which simplifies that. Let's see, P is X, R is Y, and Q is 2Z. 2 times this thing. But here we have, now we have all the pieces. We have our partials, we have the P, Q, and R, all in terms of X and Y only. Plug them in to the formula. Here's what you get as the integrand. And you get some cancellations here, which is nice. Plus 2y plus another y, it's just 3y dx dy. The integrand vastly simplifies. And then we're integrating over this rectangle. X goes from 0 to 3, and y goes from 0 to 2. There's our double integral. Easy enough. It breaks up into a product. Bada boom, bada bing. The answer is 18. So that finishes the flux integral and its surface integrals as well. But the only real surface integral we covered in depth was the flux integral. We talked about what that means earlier. Here is the definition of it. And here were the 3 methods that I taught in my class to do that. Here's the general method. If you're lucky enough and f dot n is a constant and you know the area of the surface ahead of time, you can use the direct method. I call it direct because you're just using the definition directly. And the PQR method when the surface is Z is a function of X and Y. And I could have had 2 more formulas like this, or when X is a function of Y and Z, or when Y is a function of X and Z. That ends the flux integral, and we'll cover more subjects. We're almost done with the last part of NMath A, actually.